Welcome back to Chapter 5, Part 3. So today we are going to be continuing this unit on chemical reactions and quantities. We'll actually be wrapping it up. As you recall, in our first two parts, we talked about balancing chemical equations and how to identify different types of chemical reactions. Then in part 2, we talked about the mole and Avogadro's number and how we can use that and the molar mass to determine the grams of a substance that might be needed in a reaction and convert that to moles. And then we can also go from moles to particles. And now what we're going to talk about is stoichiometry and the stoichiometric relationship that can be obtained from a balanced chemical equation and how we can use that then to calculate the number of moles of another substance in a reaction given the moles of one of the other substances in the reactions. We'll then go further and say, what if we're given the mass in grams of a substance in a reaction? How then can we calculate the mass in grams of another substance in the reaction, whether it's another reactant that we need or how much product can be made? And then from that, we can learn how to identify what's called the limiting reagent of a reaction and how to calculate the amount of product that could be formed from that reaction, and then the percent yield, or how efficient was our reaction? Did we make as much as we thought we would make? So why don't we go ahead and get started by talking about the mole relationships in chemical equations. So the first thing we need to address is something called the law of the conservation of mass. This is why chemical equations have to be balanced, and this is what's going to give what we call our stoichiometry of the reaction. So the law of conservation of mass indicates that in an ordinary chemical reaction, matter cannot be created or destroyed. Therefore, there is no change in the total mass, and therefore the mass of the products must be equal to the mass of the reactants. So, for example, when silver reacts with sulfur to create tarnished silver or silver sulfide, the balanced chemical equation shows us that there's twice as many silver atoms reacted for every sulfur atom. This is what we call stoichiometry, or the proportional relationship between our reactants to each other and our reactants to our products. So remember, the law of conservation of mass says for however many atoms we have on our reactant side, that must also exist on our product side. Remember, matter cannot be created nor destroyed. So if I have 2 silver atoms on our reactant side, well, I better have 2 silver atoms on the product side. And if you notice, we do, right? It's not individual atoms, it's atoms within the molecule of the silver sulfide, but they're still there. So that's what the subscripts and our molecular formulas and our coefficients ahead of our molecules or elements is allowing us to indicate that we are abiding by this law of the conservation of mass. And if you remember, we can go from moles of a substance to grams of the substance using the molar mass. So if I mix 2 moles of silver and 1 mole of sulfur, well, I better get 1 mole of silver sulfide out in our product. Again, this is assuming 100% efficiency, meaning all of our reactant is going to product, and it's also assuming that we can capture all of our product, right? Sometimes things are lost in the reaction, and so we'll talk about that when we talk about product yield. However, so if you go to the periodic table and you look up the molar mass of silver, and if you say, okay, if I have 2 moles of silver, well, that should give you a weight of 215.8 grams. Sulfur has a molar mass of 32.1 grams per mole. If we only need 1 mole of silver, then sulfur, then I would weigh 32.1 grams. If I mix 215.8 grams of silver, 32.1 grams of sulfur, I should get 1 mole of silver sulfide, which should weigh, if you remember how to do your molar mass calculator, it should weigh 247.9 grams per mole. Again, if you add these things together, this should weigh 247. If you have 100% product yield, then you should end up with 247.9 grams of product, right? Law of the conservation of mass. Not only must the moles be balanced on our product side and our reactant side, but the mass must also be balanced on our product side and reactant side, okay? Again, assuming we capture all of the product. Some products are gases, and if you're not careful, you may lose them into the atmosphere. And so if you're doing reactions in the gas phase, you want to make sure that you are capturing all of that gas so that you can efficiently weigh everything. Okay, so we garner a lot of information from our balanced chemical equation by understanding the law of conservation of mass, right? We can get the equation itself, which tells us the recipe and the proportional way in which we should mix our reactants and how much of our products we should get in proportionality. So remember thinking about our cookie example. Our cookie recipe is usually 1 dozen or 2 dozen cookies, but we have to know that we have to mix a certain amount of flour and a certain amount of sugar and a certain amount of chocolate chips in order to get that amount of product. If we need to make 72 cookies or 140 cookies, well, once we know our recipe stoichiometry and how much product can be made given that stoichiometry, we can scale it up or scale it down pretty easily. Same thing in the lab, right? That's what our balanced chemical equation is giving us. We can talk about our units in terms of atoms, right? So we could just take 2 silver atoms and 1 sulfur atom and mix it and get 1 molecule. Not very efficient, right? We can't sit there and pick out 1 silver atom. They're really teeny tiny. Okay, so let's scale it up a little. Okay, what about 200 atoms and 100 sulfur atoms? Well, again, that's going to be a little hard to measure out. We can't quite do that. I'm not going to sit here and count. Do I have 200 silver atoms? I can't even see 1 silver atom. How am I going to count 200? But again, you get it. The proportionality is still there. We need 200 silver atoms to every 100 sulfur atom in order to get 100 product atoms of the silver sulfide. Okay, well, let's scale it up even more. Let's talk about a mole or a mole of particles. So it could be 6.02 times 10 to the 23 atoms. Okay, now we're getting into proportional sizes that we might be able to use in the benchtop. Okay. However, again, when we're talking about Avogadro's number of atoms, that is like counting atoms, 6.02 times 10 to the 23rd. I have a hard time counting to 100 without losing my place. I'm sure as heck not going to count to 6.02 times 10 to the 23rd. And again, I have to look at the individual atoms to count them, and I can't see those individual atoms. But our proportionality exists. If I could, I would need 2 times 6.02 times 10 to the 23 silver plus 1 times 6.02 times 10 to the 23 sulfur atoms. Mix that, and I should get 1 times 6.02 times 10 to the 23 atoms of silver sulfide. Great. Avogadro's number is on the scale of which we can see it all together, even though I can't count those atoms. But what is that? That is a mole. So the other way to look at it, and probably the more relevant way for us to look at it, is in terms of moles of silver and moles of sulfur. So 6.02 times 10 to the 23 atoms of silver is a mole of silver. So I need to mix 2 moles of silver and 1 mole of sulfur to get 1 mole of silver sulfide. Again, mole is great. I can count moles, but I don't weigh moles. That's not what I don't go to the bench top and take down my jar of silver and take out a mole. I don't have like a cup thing that says this is a mole of silver, right? What I have to do instead is I have to weigh that mole. So again, if I go to the periodic table, I can see that 1 mole of silver should weigh 107.9 grams. So now I can take my jar of silver, I can scoop out some of that silver, and I can put it on a balance and weigh it, right? And so what I need to weigh is 2 times 107.9. So what I really need to weigh is 215-ish grams of silver, right? So I weigh that. Then for sulfur, I only need 1 mole of sulfur. The molar mass of sulfur is 32.07 grams. So I'm going to take down my jar of sulfur and I'm going to weigh 32.07 grams of sulfur. If I mix these two up in the correct conditions, I should get then 247.9 grams of silver sulfide. And again, I was able to figure out the molar mass of silver sulfide by going to the periodic table and adding the 2 moles of sulfur and the 1 mole of sulfur together to get the formula mass or the molecular mass of 247.9. Notice that on our reactant side, our two reactants together weigh 247.9, and our product should weigh 247.9. Now I can scale this up or down. Let's say I needed 2 moles of silver sulfide instead of 1 mole of silver sulfide. Well, then I need to double everything on my reactant side. So I need 4 of silver and 2 of sulfur. What if I only need half a mole? What if I don't need a whole mole, right? Well, then I just need to divide everything by 2 on this side. So I need 1 mole of silver and a half a mole of sulfur, and that should give me a half a mole of silver sulfide. Hopefully you get sort of how this scaling up and scaling down works in terms of chemistry. It's the exact same as it is if you were going to make cookies, right? If you only need a half a dozen of cookies, right, then you're going to divide all of your ingredients in half, right? And that's going to allow you to save some of your eggs and save some of your flour and save some of your sugar, right? All of that costs money. If you don't need a whole dozen cookies, then don't waste all of your ingredients. Make a half dozen, scale it down. If you need more, let's say you need 3 dozen cookies, well, then you got to scale everything up by 3 if your recipe only makes 1 dozen cookies. All right, so again, same thing you do in the kitchen, we do in the lab at the bench top. So let's talk about multiple factors that we can obtain from an equation. So let's consider the following equation. 2 iron plus 3 sulfur gives us iron sulfide. So we can also read this as 2 moles of iron plus 3 moles of sulfur give us 1 mole of iron sulfide. A mole-to-mole factor is a ratio of the moles for any 2 substances in the equation. So we can look at and relate any reagent to any other reagent. So for example, if we wanted to relate iron to sulfur, we would say we need 2 moles of iron for every 3 moles of sulfur. We can flip it and also say for every 3 moles of sulfur, we need 2 moles of iron. This is just our mole-to-mole factor relating the 2 reactants to each other. We can also relate our reactants to our products. So for every 2 moles of iron, we should be able to obtain 1 mole of iron sulfide if sulfur is in excess, or at least proportionally relevant. And then we can also flip it. For every 1 mole of iron sulfide, we need 2 moles of iron. We can also look from the perspective of sulfur and iron sulfide. For every 3 moles of sulfur, we'll get 1 mole of iron sulfide. And flip it. For every 1 mole of iron sulfide, we need 3 moles of sulfur. Again, this would be assuming iron is in excess, okay, and not a limiting reagent. So again, this is just our way. Our mole-to-mole factor is our way to relate any substance in our chemical equation to each other and the dependency that they have with each other, or their stoichiometric or proportional relativity, okay? All right, so why don't we review that, get some practice writing these mole-to-mole factors and getting them from the balanced chemical equation. Remember, the numbers that end up in our fraction here are just our stoichiometric coefficient that is in front of that molecule or element, okay? So the 2 comes from the coefficient for 2 in iron. The 3 here comes from the coefficient in front of the sulfur. All right, so why don't you get that practice, go back, it's not chapter 7, I apologize, it is chapter 5, on our in-class activity, and work question 11. Again, feel free to work with a friend. When you're ready, come back to the lecture. Okay, so now that we have some practice writing these mole-to-mole factors, we can now use those mole-to-mole factors in our calculations to help us predict how much of a reagent will be consumed or needed, and or how much product can be made if a certain amount of reagent is given. So for example, we could ask the question, how many moles of iron oxide can be formed from 6 moles of oxygen? Okay, so here we have our balanced chemical equation that says for every 4 moles of iron and 3 moles of oxygen, we get 2 moles of iron oxide. Now, the question is asking us how many moles of product, iron oxide, can be formed by 6 moles of oxygen. So now that we're relating iron oxide to just one of the reactants, oxygen, we're going to assume iron is in excess, meaning we don't need to worry about how much iron is there. We only care about what is the total amount of product that can be formed given this amount of our reactant. Therefore, we are going to relate the given amount of moles of oxygen using the mole-to-mole factor of oxygen to iron oxide. Okay, so the way we set up the calculation is very simple. We start with what we're given, 6 moles of oxygen. We multiply it by the mole-to-mole factor relating oxygen to that reagent, in this case, the product, iron oxide, and then we plug and chug. Now remember, if we're starting with oxygen, we want to use the mole-to-mole factor in which oxygen is on the bottom. So again, look at our coefficients. For every 3 moles of oxygen, we should get 2 moles of iron oxide. Therefore, our mole-to-mole factor should be 2 moles of iron oxide for every 3 moles of oxygen. Remember, just slide your coefficients there in front of that reagent. Notice our dimensional analysis that moles of oxygen cancel, and we are left with moles of iron oxide, which is what we are asked to calculate. And so now all we have to do is plug and chug. So 6 times 2 divided by 3 gives us 4. So if we are given 6 moles of if we are given 6 moles of oxygen and we assume iron is in excess, we can theoretically make 4 moles of our product, 4 moles of iron oxide. Okay? So here's another handy flow chart that will help us in terms of doing these types of mole-to-mole factors. I have a version of this also on Canvas that you'll be able to use on your exam as well. But basically, we can start to predict how much of a substance is produced or needed in a chemical reaction using this flow chart. If we are given the known substance in moles, we start here and we multiply by the mole ratio to get the moles of our unknown substance or substance B. Sometimes, however, we are given grams of a known substance, so we need to go back a step. So if you're given grams of a known substance or substance A, the first thing you need to do is divide by its molar mass in order to get to moles of our known substance. Then we can multiply by our mole factor to get to the moles of our unknown substance or substance B. Sometimes our questions ask us to calculate, well, how many grams of B can be made? So then we go another step further and we multiply by the molar mass in order to get to grams. So this flow chart will help you with that basically conversion or that step plan that you may need to sometimes make in a more complex calculation, right? So if we're starting with grams of A, we divide by the molar mass to get to moles. Then we multiply by the mole ratio to get to moles of B. And then if we need grams of B, we would then multiply by the molar mass of B. Okay, and we can go both backwards and forwards. Just look at your arrow and make sure you understand, are we dividing or are we multiplying based on the direction? Okay. Sometimes we may be asked to do particles, right? How many atoms or number of molecules are needed? Well, in that case, you're going to use Avogadro's number in your conversion to get to moles, not grams or molar mass, okay? When we start talking about gases, this is where this one will come in if we go from a liters of gas, but we haven't talked about that yet, so you can basically ignore this middle line here. We'll talk about that next time or in chapter 6, okay? But for the most part, you're going to be dealing with doing either mole to mole conversions, which is just a nice one-step conversion, grams to moles conversions, or grams to grams conversions. And you may also be asked to do particles to moles, or particles to moles to moles to particles. Okay, but either combination, you should be able to figure out your path using this flowchart. All right, so let's do some practice. How many moles of iron are needed to react with 12 moles of oxygen given this balanced chemical equation. 4 moles of iron plus 3 moles of oxygen gives us 2 moles of iron oxide. Okay, so step 1 is to state the given and needed quantities and to analyze your problem. Again, first thing here, always make sure that the chemical equation you're given is balanced. It's not always balanced, so that's always the first thing you need to do in this type of calculation is make sure you're balanced. Okay. Analyze the problem, right? So state your given. We are given 12 moles of oxygen. Our needed is the moles of iron. Our connection is going to be our multimole factor for oxygen. So again, if we go back to this little flow chart, we're given the moles of our known substance, which is oxygen in this calculation, okay? And we are asked to calculate the moles of our unknown, which is iron. So our connection here is our mole to mole factor or our mole ratio. We don't need to worry about molar masses here because we're only going from moles of known to moles of unknown, right? It's just a one-step calculation. Okay? And our other information that we're given that we need in order to create that mole factor is our balanced chemical equation. So we're going to look at the coefficients that are in front of those reagents in order to develop that mole factor. Our next step is to write our plan to convert to our given to the needed quantity. Is it moles or is it grams? Remember to check the conversion map if you need help here, which is this map right here. So we're going from moles of our known to moles of our unknown. So it's just a one step. All right. So our conversion is going to be moles of oxygen to moles of iron using the mole to mole factor relating oxygen to iron. Therefore, we need that mole to mole factor. So use the coefficients in our balanced chemical equation to write our mole to mole factors. We should have two, okay? We should relate iron to oxygen and oxygen to iron. So for every 4 moles of iron, we need 3 moles of oxygen. 3 moles of oxygen. And then again, we can flip it. For every 3 moles of oxygen, we should get 4 moles of iron. All right, now the question is, which mole to mole factor do we need? Do we need the mole to mole factor where oxygen is on top or oxygen is on bottom? Well, remember, we're converting from oxygen to iron. Therefore, we will want to use the mole to mole factor in which oxygen is on bottom, so oxygen cancels out. So now step 4, set up our problem, plug in our actual numbers here in order to do this conversion. So start with your given, 12 moles of oxygen, multiply it by the correct mole to mole factor. Make sure your units cancel out so that you know which mole to mole factor to use, and then plug and chug. So 12 times 4 divided by 3 gives us 16 moles of iron is needed if we have 12 moles of oxygen. All right, so again, it's just like if I have 4 eggs and how much flour do I need to make for this recipe, okay? That's basically the same thing we're doing here. Okay. All right, so your turn. Why don't you go back to Mastering Chemistry and work question 12 now. When you're ready, return to the lecture. All right, so why don't we practice now doing a mass to mass calculation? So we've done the mole to mole, very simple one step, but what if we are asked to do a mass to mass calculation? So a question might look like this. Suppose we want to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen in the following reaction. Nitrogen plus hydrogen gives us ammonia. Now note that this equation is already balanced, so we don't need to balance it, but remember it may not always be balanced. So in this case, we're not starting here in the middle of our conversion table like we did in the last calculation. Now we're going from grams of a known substance, and we're asked to calculate all the way to grams of our unknown substance. So we're going to start back here, and we're going to do 1, 2, 3 steps to get to our answer. Okay, not 1 step, 3 steps. All right. So let's work through that together. So step 1, state the given and needed quantities. This time it's grams. Also make sure your chemical equation is balanced, which it is. If you notice, we already have our coefficients here in front of our reagents and products. That's our first sign that it's balanced. Always good to double check just to make sure. And then state your given and needed, right? So we are given 32 grams of nitrogen. We are asked to calculate the grams of ammonia. So for that, if you go back to that flow chart, we're going to need both our mole to mole factor and the molar masses of each reagent and product, okay? So our next step then is to write our plan to convert the given to the needed quantities. Again, refer to that conversion map if necessary, but the plan you should get is this, starting with our known substance A, which is N2. We're going to start with grams of N2. We need the molar mass of N2 to convert to moles of N2 or nitrogen. Then we need the mole to mole factor relating ammonia to nitrogen to go to moles of ammonia. Once we're in moles of ammonia, we then go to the molar mass of ammonia, or use the molar mass of ammonia to get to grams of ammonia. Again, if you don't know where that came from, just scooch on back to that flow chart that I gave you. And we're starting here, grams of our known substance. We're going to need the molar mass of our known substance to get to moles. So in this case, it's grams of nitrogen, molar mass of nitrogen to give us moles of nitrogen. Then to hop over to ammonia, we need our mole to mole factor or the mole ratio. Again, that's from the coefficients of our balanced chemical equations to get from moles of nitrogen to moles of ammonia. Once we're in moles of ammonia, then we need the molar mass of ammonia to get to grams of ammonia. Okay, and remember guys, these molar masses come from where? Right, the periodic table. Okay, so don't forget, and don't forget your subscripts in your molecular formulas to calculate the right molar mass for your molecule. All right, don't forget that. The subscripts are important. Okay, so let me scooch back on. There we go. All right, so step 3 then is to get all of the little things in the arrows that we need. So we need our coefficients and we need our molar masses, okay? So the coefficient, again, is going to come from our mole to mole factor is going to come from the coefficients of our balanced chemical equations, and the molar masses is going to come from the periodic table and the molecular formulas that we calculate using the elements of the periodic table. Okay, so our 2 molar masses that we need the molar mass of nitrogen gas. So notice it's N2, so it's going to be 2 nitrogen atoms, so it should be 28.02 grams for every mole of nitrogen gas. And we can write those conversion factors 2 ways, right? 1 mole of nitrogen gas for every 28.02 grams of nitrogen, and flip it, 28.02 grams of nitrogen for every 1 mole. The molar mass of ammonia is going to be 1 nitrogen plus 3 hydrogens, which should give you 17.04 grams. And again, we get 2 conversion factors there. 1 mole of ammonia for every 17.04 grams, and 17.04 grams for every 1 mole of ammonia. And then finally, our mole to mole factor is given to us from the balanced chemical equation and the coefficients. So for every 1 mole of nitrogen, we need 2 moles of ammonia, right? 1 mole of nitrogen, 2 moles of ammonia, and we can write those 2 conversion factors as 1 mole of nitrogen for every 2 moles of ammonia, and 2 moles of ammonia for every 1 mole of nitrogen. Remember, which one do you use? Well, it's whatever you're converting away from. So whatever is preceding our arrow, that is what should be on the bottom. So in setting up our problem, right, our first step is to write our given, so 32 grams of nitrogen, and then use the conversion factor for the molar mass of nitrogen. If nitrogen is preceding it, then we need nitrogen on the bottom. So we are going to use this one. We're going to divide by the molar mass, okay? And then we just kind of keep stepwise plugging and chugging in. So if we set up the problem, you should get something like this. So starting with 32 grams of nitrogen, we're going to use the molar mass factor, in which the grams of nitrogen is on the bottom, so that grams of nitrogen cancel. In our next step, we need our mole to mole factor relating ammonia to nitrogen. Again, we're converting away from nitrogen to ammonia, so we need nitrogen on bottom. So that means we're going to use this mole to mole factor conversion, where 2 moles of ammonia for every 1 mole of nitrogen. And then finally, our third step is we need to use the molar mass of ammonia. Well, this time we're trying to get away from moles of ammonia into grams of ammonia. So we want to use the molar mass factor, in which grams of ammonia is on top and moles of ammonia is on bottom, right? Because moles is what's ahead of it. So that's what we want to cancel, so that we are left with our units in grams of ammonia. Again, use dimensional analysis, make sure your units cancel, and that you are left with only the unit you are asked to calculate, or your needed unit, in this case grams of ammonia. Okay? Now all we have to do, once our problem is set up, we can plug and chug. So it'd be 32 grams divided by 28.02 times 2 times 17.04 equals 39. Okay? Again, making sure all of our units cancel so that our problem is set up right, and we are only left in the units of what we are asked to calculate, which is grams of ammonia, grams of ammonia. Boom, we are good. All right, so why don't you guys practice this by working question 13 on mastering chemistry. All right, when you're ready, return to the lecture. All right, welcome back. So now that we've talked about stoichiometry and how we can predict how much product can be made or reagent is needed given another reagent, either in terms of moles or grams, let's now talk about limiting reagents. So what is a limiting reagent and how can we use it? So in order to do this, I think the best way to introduce this problem is through our lab. Limiting reagents and s'mores. All right, if you want to make this extra fun, pause, run to the grocery store, get everything you need to make for s'mores, and then when you're done, you can celebrate. So what we're actually going to be working through in this is your lab assignment. So if you want to sort of pause this and wait to do this tomorrow, that will be fine, or on the day that this lab is assigned. But if you're sort of in the groove and you want to get a head start, go ahead and work through this with me. So what I want you to do right now is to pause the lecture, go to Canvas, get the assignment, limiting reagents and s'mores, print it out or have it on your computer screen, and go ahead and answer questions 1 through 8 from this worksheet. Okay, again, a copy of this can be found. And remember, you are going to turn this in as your lab assignment. All right, when you're ready, you finish number 8, come back to the lecture. Okay, so hopefully you've completed questions 1 through 8 on that limiting reagent s'mores handout. And so you already have a good idea of what a limiting reagent is, but I just want to circle back as a group and define it all together. So a limiting reactant or a limiting reagent in a chemical reaction is the substance that is used up first. It limits the amount of product that can be formed. The reactant that does not completely react and is left over at the end of the reaction is therefore called the excess reagent. So a great example of this is hot dogs and hot dog buns. There is never enough hot dog buns for the amount of hot dogs you get. So you always have to cut up the last couple hot dogs and use them in beanie weenies or something like that. But you get the idea, right? If we have less hot dog buns than we have hot dogs, then the hot dog bun is our limiting reagent. If we only have 4 buns, we can only make 4 hot dogs, and therefore our excess reagent is the hot dog wiener, and we're going to have 1 excess wiener. Again, that can be used in beanie weenies or some other recipe. Okay? So in many reactions, there is a limiting reactant that determines the amount of product that can be formed. This happens all the time in the chemistry world. Given a chemical reaction from each reactant, we can then calculate the amount of product possible when it is completely consumed and determine the limiting reactant. That's the one that runs out first and produces the smaller amount of product. So as chemists, this is how we determine our limiting reagent. We predict the product that can be formed from all of our reactants, and whichever reactant produces the least amount of product, that is what we consider as our limiting reagent. For example, if we go back to our hot dog example, if we assume the hot dog is our limiting reagent, then we should be able to make 1, 2, 3, 4, 5 hot dogs. If we ignore the hot dogs and assume the buns, then we can only make 1, 2, 3, 4 because our reaction stoichiometry is 1 to 1, right? We need one of each in order to make a full hot dog. Since the buns make less product, less hot dogs, it is our limiting reagent, okay? 4 versus 5, right? So that's sort of how we predict our limiting reagent. So let's do some practice. If 3 moles of carbon monoxide and 5 moles of hydrogen gas are the initial reactants, how many moles of methanol can be produced and what is our limiting reactant? So here we're given our balanced chemical equation. I know it's balanced because I'm already given a coefficient. If I wasn't given a coefficient here, I would double check, right? Always check to make sure that your chemical equation is balanced. All right, step 1, state the given and needed quantities, moles here, and ensure that your chemical equation is balanced. So analyze the problem. We are given 3 moles of carbon monoxide, 5 moles of hydrogen. We're needed to identify how many moles of methanol can be produced from each of our reactants, assuming the others in excess. So we're only looking at it the perspective of one reactant at a time. And then from that, predict our limiting reagent. So for this, we're going to need our mole-to-mole factors, just like we did earlier in the lecture here. But instead of just looking at one reactant, we're going to look at both reactants from the perspective of each other, ignoring the other. So we're going to do basically 2 of these calculations, okay? We also need our balanced chemical equation. All right, so the next thing is to write a plan to convert the moles of each reactant to the moles of products, right? So we're doing 2 calculations here. First, we're going to look at the perspective of carbon monoxide. So we're going to relate carbon monoxide to moles of methanol, and we're going to look at the perspective of the hydrogen gas. So we're going to convert moles of hydrogen gas to moles of methanol, both using the mole-to-mole factor for each other. Okay? Now we need to use coefficients to write our moles-to-mole factors, so the coefficients from our balanced chemical equations. So for carbon monoxide, it's a 1-to-1 relationship, right? For every 1 mole of carbon monoxide, we get 1 mole of methanol. So we can get our 2 conversion factors here by doing that one equality. For hydrogen, our relationship is a 2-to-1 stoichiometry. So for every 2 moles of hydrogen gas, we produce 1 mole of methanol. And from that, we get our 2 conversion factors written opposite each other. Okay, the next step then is to calculate the quantity in moles of product from each reactant. And we're going to do this one at a time, assuming the other reactant is in excess. Once we have calculated how much product can be made from that reactant, assuming the other is in excess, then we select whichever one is the smaller product forming reactant, and that is our limiting reagent. So doing that, start with what you're given for carbon monoxide. So 3 moles of carbon monoxide multiplied by its mole-to-mole factor, 1 mole of methanol for every 1 mole of carbon monoxide. Again, I know carbon monoxide's on the bottom because that's what I'm converting away from. So that's why I'm using this second mole-to-mole factor, conversion factor. Okay, so 3 times 1 divided by 1 gives us 3. Now from the perspective of hydrogen, we are told that we have 5 moles of hydrogen, but here our mole-to-mole factor is 1 to 2. So it's going to be 5 times 1 divided by 2 gives us 2.5 moles of methanol. Now, the question is, which one's our limiting reagent? Well, it's whichever one produces the least amount of product. So carbon monoxide can produce 3 moles, However, the amount of hydrogen gas we're given can only produce 2.5 moles of the product. Therefore, dihydrogen gas or hydrogen gas is our limiting reagent because it makes the least amount of product, assuming the other reagent is in excess. Okay, so 2.5 is smaller than 3, therefore hydrogen is our limiting reagent. And the maximum amount of product we can make is 2.5 moles of methanol. So we are going to have excess carbon monoxide remaining in our reaction vessel. Okay, so now that we know how to predict our limiting reagent and therefore predict the total amount of product that can be made, now we can talk about reaction yields. So when the reaction does not go to completion or some of the reactant or product is lost, the amount of the product produced may be less. So for example, in this calculation, we predicted that we could make 2.5 moles of methanol. However, maybe we lost some of that. So maybe we actually only made 2 moles of methanol. That means we're going to have less than 100% product efficiency, right? We're going to have a smaller product yield. So in order to calculate that, we need to understand 3 key words here. Theoretical yield. Theoretical yield is the maximum amount of product which is calculated using the balanced chemical equation. So in this reaction, if I mix 3 moles of carbon monoxide, 5 moles of hydrogen gas, I can only make 2.5 moles of methanol, right? Because hydrogen gas is my limiting reagent. That's the maximum amount of methanol that I can make. So that is my theoretical yield in this example. The actual yield is the amount of product that is actually physically obtained at the end of the reaction. Maybe some of that methanol got lost. Maybe the reaction didn't go all the way to completion, right? So my actual yield, maybe it's 2 moles, okay? That's my actual yield. That's what I actually get. The percent yield then is the ratio of the actual over the theoretical. So in my example, it'd be 2 moles of methanol over the theoretical 2.5 moles times 100%. That's my percent yield. And you'll notice it's less than 100. It is almost always less than 100. Most reactions do not go to completion and we lose things all the time. Good yield might be 80%, 70%, right? It's almost never 100%. Sometimes it's over, and that's because there's something still trapped in there, like water or something else. But usually 9 times out of 10, it is less than 100, and sometimes way less than 100. And this is a big issue when we think about sustainability in chemistry. If we want to be green chemists, we want to make sure we get as close to 100% product yield efficiency as we can in order to ensure that we are utilizing all of our resources as efficiently as possible and minimizing energy impact on our infrastructure. All right, so why don't you go back to the lab activity, limiting reagents and s'mores, and now work questions 9 through 14. If you need more practice, work exercises 1 and 2 at the end of the activity. And don't forget to submit the copy of your work to the Canvas lab assignment, s'more limiting reagent worksheets, because this does count as your lab for this unit. Okay, if you have any questions, feel free to circle back with me. Don't forget you can book an office hour with me, or it doesn't have to be a full hour, right? It can be however long you need to answer the questions that you may have. Just email me and I'll be happy to set up that appointment with you over Zoom. All right, hope you guys have a great rest of your day, and hopefully you are enjoying a s'more at home. All right, bye guys.